In this example, we are given something without any context. We're just told that there were n trials and that the probability of success is p equals 0.75. If we assume that we're dealing with a binomial random variable here, then we're supposed to come up with the binomial probability distribution. Okay, let's see here. So we need to use this formula. That's actually just one option on the TI-84, and I'll show another briefly after we've got all the values. Okay, so remember that there's a total of n trials, in this case 10, and little p being the probability of success. In filling in that table, they're giving us different values for how many successes there could be. You're raising the probability, of success to the number of successes times the probability of failure to the number of failures, so that you have this total of n here. The sum of the bases, by the way, is 1. And then since we don't care in what order the successes occurred, just that we have that number of successes within the total of n trials, then we need to multiply by NCR, the number of combinations. When you have n things available, you're going to choose R of them without any repetition and no arrangement. That is also referred to as the binomial coefficients. All right, so R is going to be ranging, since we're filling in the entire probability distribution, but n is 10, p is 0.75, and 1 minus p, then that would be 0.25. What I'll be doing on the TI-84 is wherever R showed up, I'm going to be putting those possible values of the random variable x, so the R's there, into list 1. Okay, here we go. And then I'll show you a shortcut here briefly. Let's see. All right. So get this to show up nicely. Here we go. They want these probabilities rounded to 4 places. So here we go. Got to clear out some old data here. Since n was 10, you could have as little as 0 successes all the way up to 10, but you're counting because a binomial random variable is a discrete random variable. 5 ones. And let's see. All right, so go to the very top of that list 2, press enter, and then we can put in the formula. So that's going to be 10C L1. And it might be a good idea, at least on the older calculators, to type parentheses around that binomial coefficient. So we're grabbing values from L1 times, okay, 0.75 to the R power. Again, the values of R are in list 1. Oop, that was not what I wanted. Clear that out. Okay, so 10 C L1 times 7 to the L1. Scroll to the right on these newer calculators. Get out of the exponent before you type in the next part. 0.25, 0.25 raised to the power of 10 minus R, so 10 minus L1. All right. On the newer calculators, This is not needed, but on the older ones in the exponent, you'll want parentheses around this. Minus L1. Close that parenthesis. Might not have had a parenthesis there. Okay, one more time. No, get out of it. Okay, parentheses 10. L1 times 0.75 to the power of whatever is in L1 times 0.25 to the power of whatever 10 minus L1 is. Sorry, 10 minus L1. There we go. All right. Now it can only show so much in the column. So you can scroll down here to see things more exactly, going much further. That first one, that E-7 is standing for times 10 to the -7. So that 9 is not showing up until 7 places after the decimal point. When we're only going to 4 places, that's going to round to 0. And then when R is 1, or as the author is putting it, little x, that 2 is not showing up until the 5th place after the decimal point. So that's going to round down to 0. This does not mean they're impossible, but they are very unlikely. And because of the rounding, we're saying 0. When x is 2, okay, times 10 to the -4, we're seeing 0.00038. And that's going to round up to 0.0004. When R is 3, that's rounding to 0.0031. My zeros there. When R is 4, that's rounding down to 0.0162. And when it's 5, it's rounding up to 0.0584. Notice how these keep going up for a while. 7, that's rounding up to 0.1460. And I expect this one's also going to be higher than the last one, but then when we get to 8, it's probably going to start going down again. 0.2503 is what that will round to. .2816, that did go up. Maybe the last two will be lower than that. 0.1877, that is lower. Finally, 0.0563. All right, let's read again. You should definitely round down to 0. sure which one it is. Let's see what happens. Didn't like my answer for 3. Very strange. Oh, looks like I just had 2 dots there. Okay, we're going to next compute the mean and standard deviation by what we learned for random variables in general. And that we can take for the mean score, which is in list 1, times probability, which is in list 2. And then we're going to want the sum, because remember that in general, for a random variable x, it is the sum of the scores times the probability of the scores. Or if we go with what I was writing here, there should be a capital P. Right, so let's see here. We need the sum then of what I just created in list 3. So I can go to stat again, calc, 1 variable statistics, and tell it to work from list 3. And our sum is 7.5. This gives a particular version of the formula for standard deviation, but really that doesn't matter. We could use the other formula. So we go to list 4, and we're going to take each of those scores in list 1. List 1 minus, let me first remind you of the formula that I'm using. So we're taking scores minus mean, squaring them, and multiplying them by the probability of the scores. That'll give you the variance. Then when you take the square root, you have the standard deviation. All right, so list 1 minus 7.5 for the mean, squaring that, and then multiplying by the probabilities that were in list 2. We need that sum, and then we're going to take the square root of that. So here's what we can do. Square root, second and stat. Under the math submenu, go to sum, and this was in list 4. They want this to be rounded to 2 decimal places. So that would round up to 1.37 when we round to the hundredths. Now notice that 7.5 we got for the mean, that was n times p. This formula works for any discrete random variable. This formula works just when you're dealing with a binomial random variable, but we still get 7.5. And then to compute the standard deviation, showing you the formula there, excuse me. Well, we've already computed what n times p is. And in computing probabilities, we got 0.25 for 1 minus p. We need the square root of all of that, according to this formula. So square roots of 7.5 times 0.25. And that is the same answer we came up with using the more general approach. Now, graphing this, before we do that, I want to show you something real quick. Back up here, we found that the probability of x equaling 3 was approximately 0.031. And I want to show you something else that we could have done on the calculator. We could press second, and above vars is DISTR, short for distributions. Scroll down, and there are two options for binomials. In this case, we want the first one. The second one is for cumulative distribution function, where you're adding up for different values of r, little r, or as the author calls it, little x. PDF is for a single point, a single value of, in this case, the calculator is matching up with what the author has. We had 10 trials. Probability of success was 0.75. And we're talking about an x value of 3. Let me bring up both this and this. So when rounded to 10 thousandths place, 10 thousandths place, 4 places after the decimal point, we should be getting 0.0031. And that's what we're seeing this way as well, rather than using this formula. Okay, so the graph, let's look at what we came up with here. Things were going up, 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 until we got to 8, which, by the way, was close to 7.5, and then it dropped. And the only place I'm seeing that is with the first choice. You could zoom in, look at the choices, you know, the different heights a little more carefully and compare to this, but I believe that's going to be our answer here. And that is skewed left.